Right. Okay. So what I'm going to go through to start with, the first bit is a little bit fiddly. I'll try and explain it clearly, but do query me if you're not sure on what I'm talking about with some of the bits and pieces. So what we're going to try and do, if you remember, hopefully you do from the previous weeks, we solved lots of sets of linear equations. So what we're going to try and do this week is to convert a differential equation, an ordinary differential equation, into a set of linear equations that we can solve. So this is a practical numerical technique. It's also the basis of a technique that the physicists will come across in sort of quantum mechanics, the sort of Heisenberg version, the matrix version of quantum mechanics. So it's a little bit similar to that. It's a way of converting from this differential equation and this sort of continuous infinite dimensional space into something that's a bit more tractable. So what I'm going to focus on this lecture, this first bit, is how we can represent differential operators as a matrix. I think that's a sort of slightly odd concept maybe to some people, but we can try and do this. So maybe from a week or two ago, going back to calculus in year one, the idea that you can approximate a derivative at some point by the values of the function near the point of interest. So if you've got two values of the function somewhere near where you want to estimate its derivative, so if you have 2 points close by and divide by the distance between the points, then you have an approximation to the derivative. So it's basically the slope of the function at that point. Now, if you remember the actual definition of the derivative is then that you take the distance between the points infinitely close. So you take a limit, and you should have a well-defined limit, which is the definition of the derivative. Here we're going to do everything numerically, and we're going to start out looking at second-order differential equations. So we need some estimate of the second derivative operator at some point. Just check I'm not missing. So, before I go into any more detail here, let's just talk about what we're going to do. We've got an x-axis. We've got an ordinary differential equation. So I'm going to say that means it's a function of a single independent variable. So we've got an x-axis which goes along the x-axis, and in the original formulation of our differential equation, this x is going to be our independent variable, and it can take on any values whatsoever. Though the equation may be defined between over some domain, but we're going to within that domain it can take on any values. But we're instead going to divide up our x-axis into a set of evenly spaced points, and everything we're going to talk about is going to be on those values. So instead of having a sort of a continuous x going between 0 and 3 in this case, we're going to have a set of x points. So x0, x1, x2 up to xn minus 1. So we've got n points. They're going to be separated by a distance dx, and we're always going to work with data on those points. And I'm not going to prove it's in a proper sort of mathematical sense, but for certain classes of functions, as long as they're smooth enough, what you can show is that the results of these type of approximations, these finite difference approximations, will converge numerically quite rapidly to the true values of the function that you're solving for at these x values as you make this dx smaller and smaller. So if you add in more and more data points between 0 and 3 so that they get spaced a little bit less far apart, as you do that, your calculation will become more and more accurate, and the values of your function that you're going to evaluate only at these grid points will tend towards the actual solution of the full solution. One small sort of gotcha that I will point out. So if you think you've got a fence with the fence posts, and then you've got the panels in between, you're going to have one more, at least for a standard way of building a fence, you're going to have one more fence post than you have panels. So you build the panel, you stick it between two fence posts, and then you've got one at the end. So when you want to calculate the distance, this dx, it's going to be the distance divided by n minus 1. So you're dividing by the length of the panels, not sort of the number of fence posts you've got. I don't know if that makes sense. Draw a diagram and make sure you get it right. As n gets quite large, as you've got a large number of data points, it's not going to make much difference, but it is an easy mistake to make. So, okay, so that's very long-winded. So we look at the x range that's in the original problem. We divide it up into n data points, each spaced apart by the domain we're looking at, the width of that divided by n minus 1. And if we want to find the x value of any of these x points, we take the minimum value and then we add on the I lots of delta x, which is what this is. So this dx is the limit, the upper limit, lower limit divided by n minus 1. So the x1 point is x0 plus delta x. x2 is x0 plus 2 delta x, etc. Now, what are we going to do to calculate the second derivative operator? Well, let's estimate the derivative of our solution, our y. So I'm writing my differential equation in terms of d2y dx2 equals something, or something along those lines. So the derivatives are the function y, which we're solving for essentially. We want to find out what y is. If you think back to differential equations, we want to know what function y satisfies this equation. So our first derivative of y around the point xi, so I could be 7 for instance, so it's the derivative of this function at this point. And we can approximate that using finite differences. So this is finite difference approximation to differentiation by first principles. So I'm going to write it in a slightly unusual way, so-called centered difference. So to estimate the first derivative at this point xi, I'm going to evaluate my function y at I plus some delta x that I can vary divided by 2. So that's going to be my function at the upper distance, and then I can subtract the function the function y at I minus delta x upon 2. And then I'm going to divide by delta x. The distance between the two points along the x-axis is delta x. That's called a centered difference because I've gone plus and minus delta x. There's a so-called forward distance where you go forward delta x and you evaluate the function on the data point, and a backward one, which is the opposite, where the upper point is on the data point and the one behind is at I minus delta x. So that is my first derivative. And then I plug it into the definition of a second derivative. So the second derivative is going to be the difference between the first derivative at x plus delta x upon 2 minus x minus delta x upon 2. So it's the same thing, but the function I'm plugging in here is the first derivative. Does that kind of make sense to people? So I've got the first derivatives above and below the data point, and then I divide by the distance, my delta x. And when I plug in this expression for the first derivative into here, and I consider I've gone up by this bit and down by that bit, some terms cancel out, some add up, and what I get left with is an approximation to the second derivative at the point xi is minus 2, the value of the function evaluated at that data point, and then I add on the values of the function either side of it, and I've got a delta x squared because I've got a delta x from the first derivative definition, and then the difference of those divided by delta x. I've got delta x squared at the bottom, and that's a so-called central difference approximation to this second derivative at that point. Does that make a little bit of sense to people? It's probably worth writing that out on paper for yourselves and things. There's another way of doing it, which is to do the forward difference version and the backward difference version and average them, and that will give you the same result for this central difference approximation. Now, that is the expression for the second derivative at the point I, so the xi value, and the corresponding result for the second derivative of y at that point. And my normal differential equation, which is just going to be whatever, second derivative of y is equal to, I don't know, some constant or something like that. So this equation, okay, I'm going to check on my shoelace otherwise, should be true for all the values of xi. So for all the different points along the graph, my second derivative equation should be true. So I can write this in matrix form. Ignore the top and bottom rows, but this second equation, this second row here, is going to read x0 minus 2y1 plus y2 divided by delta x squared. That's going to be the second the value in the second row once I multiply this out. So I've got a row vector, a column vector with my unknown y values. So we don't know what y is, that's what we're solving for. We don't know what they are, but if we multiply this out, the second row is approximately this second derivative at the point x1. The third row, I get so I get this 1 in the second line, so it's 1 minus 2y2 plus y3 here, and that's approximately the second derivative at x2. So each line of this gives an approximation to the second derivative evaluated at each of the data points as we go along. And so then we can equate it to a right-hand side if we evaluate whatever the right-hand side should be. So y at x is equal to c, some constant at a value x. So constant, something that's changes a function of x. So if I've got an equation that looks like this, the second derivative of my unknown function defined on some domain in x with respect to x is equal to some function of x, I can write it out like this. I've got my left-hand side, again, ignoring the top and bottom rows. The top and bottom rows are different, and we're going to use this to build in our boundary condition. But all of these middle rows, each row, when you multiply it out, is just approximately the second derivative at that point along the x-axis. And so at the point 1, this approximation to the second derivative at x1 should be equal to my value of this right-hand side, this g, evaluated at x1. And I've multiplied through by delta x. If you remember, on this thing, because of the finite difference approximation, I was divided by delta x squared. I've multiplied through, because delta x should be quite a small thing. You want the data points to be quite close together. So you don't want to be dividing by a small number, because it will tend to sort of slow and create some numerical. But depending on what your axes are like and so on, you could move this delta x, you could divide both sides through by delta x and then take 1 over delta x on both sides. But each row of this equation, this particular matrix, and we could add in first derivative terms and stuff by similar finite differences. When we multiply this by our column vector of y values, I get an approximation for the second derivative at this point, and the equation says that that should be equal to this function of x at the same point. So we've set it up. It should be true at all of these data points. That's what the equation says. At any point x within the domain that this is defined upon, this equation should be true. Let's call it G as well here, just to be. And apart from the top and bottom rows, we know how to do this. We know how to set up a matrix, or pretty much how to set up a matrix. So it's an n by n matrix, where n is the number of data points, the number of points we've cut our x-axis into. Apart from the top and bottom rows, we've got 1, -2, 1. So the -2 is on the main diagonal, and then we've got 1s either side of it. So we can set up this matrix. There's an unknown column vector, and there's a right-hand side, which I don't know if this is obvious, but this is known. We were told to solve this equation, and we were told what g is, what this right-hand side would be. So we can evaluate g at any value x, and just plug it in and build a column vector with g at the appropriate values, multiplied by delta x squared. So we can set that up, and then that's just a set of linear equations, and we use Gauss elimination to solve for the unknown vector. And that unknown vector is just the numerical value of y at each of the data points. So it is our numerical approximation to the solution. The only thing I've got left to deal with is the top and bottom row. and that's where we build in our boundary conditions. So I'm doing this for the specific case of this second order differential equation. So you may remember that there should be two conditions, two boundary conditions that should be included in the equation to make it well defined. And what I'm going to work with is that the values of this function y that we're looking for should be defined on the left and the right side of the problem. So if I look at my first row, it's only got this -2 on that main diagonal element and nothing else. So that means that only this y0 value is affected. So it just says y0 is equal to, and on the right hand side I'm going to say -2, which is only just so that this -2 here cancels out. I can divide this original equation on both sides by -2, is equal to yl, which is my boundary condition for the left side that I want to build in. So it's going to tell me that y0 is going to be equal to yl. So on my right hand side, this matrix that I specify, everything apart from the top and bottom rows is the value of this function that we're given, evaluated at the different x values. But the top and bottom rows are -2 lots of what this function should be at the left and right hand side, which should be told us in the question. That should be the boundary conditions of the question. But because this y0 is fixed, it does come into the next equation, because this approximation for the second derivative at point 1 is y0 minus 2y1 plus y2. So this fixed value does feed into this set of equations. So to make them true, this boundary condition kind of gets baked in, and we get the results. So this left-hand side, this is for this particular example where we've got a second derivative of our unknown function. In this case, there's no first derivative term, but you could make an approximation similar to what we've done before and just add in terms of this y column vector. Let you think about that. We can go for examples of that. But this is just working on that second derivative version. And then the right-hand side. Then we do Gauss elimination and we get an approximation to y at all these values, and then we can solve for it. So I think these just repeat what I've gone through, sort of pointing at it. So if I have an equation, the second derivative of y is equal to x on the interval 0, 1, then so it's this previous example I've given, but g of x is just x. My yl, my left-hand boundary condition, I'm going to say should be 0.2, and the right-hand value should be 1.5. And I could try discretizing it with different number of points. So discretizing, I just mean that it's, instead of being continuous, it's at this discrete set of points. So my matrix equation is going to look like this. I've got my standard matrix for my second derivative matrix, my unknown y thing, which is going to be the solutions that's going to come out of my Gaussian elimination, and then the right hand side is going to be -2 times the left hand side boundary condition, which is 0.2, -2 times the right hand boundary condition, and then in between I've just got my x values multiplied by delta x. So I can set up this matrix here, I can set up that column vector there, I can put it into my Gaussian elimination solver or use the NumPy solver or whatever solver you want to use, and the solution will be, if you haven't made a pig's ear of it, will be that y vector. So there you go. that means numerically you can solve any second derivative order of any ordinary differential equation that's basically a second derivative is equal to some function of x. Don't need any new code. We don't need anything new. It's all there. And we could add in terms that are first derivatives or functions of y. We just have to think how we would adapt this equation, our matrix on the left-hand side. So if we've got some constant times y, we're just going to add in a k delta x squared term. I'll leave you to multiply it out and convince yourself that that works. First derivatives, again, can be put in some form or other. Try it, check it, make sure you're sort of happy with that. Oh, I've not updated. But have a go at these examples, see if you can code them up, see if you get stuff. Then I'll leave you to build your own question. Think of a second derivative, like the second derivative of x squared is equal to sine x or something. Something you know what the solution would be. Code it up and see if you can get the numerical solution coming out. That's it. Particularly, I'm going to say that this other stuff is there as extra reading. I don't want to go into it today. Or probably this year, but it's extra reading you can have a look at. Okay, so I'll stop that.